let me give you the family of reversible gates. So the first of these that we'll use a lot is called the C0, or controlled NOT. X and Y, X goes to X plus Y, and this is an exclusive OR, so addition modulo 2. Another one of these is called the Toffoli gate. Tom Toffoli, who's now a professor at BU, used to hang out here at MIT a great deal, X, Y, and Z, and we get as an output X, Y, X and Y, so that's XY multiplied plus Z modulo 2. And then the Fredkin gate comes along. And this we draw like so with two crosses, because this gate does two wires and two crosses is a swap gate. So X, Y, Y, X. Here we have X, Y, Z. And the idea is if X is 1, then it causes Y and Z to swap. So it's X times Z and X times Y. But if X is 0, then it stays unchanged. So X bar Y, X bar Z. OK. So we have a bunch of these gates. And I want to quickly give you some theorems about these gates. First, they're universal. They're universal for all computation because they can be used to construct the AND and OR gates. First, the Toffoli gate is universal just by itself. It doesn't need any other kinds of gates along. That's really easy to see by construction. So I will take X and Y and 0. And this is XY. I can also take my Toffoli gate and put an X and a 1 and a 1. And this gives me X, 1, and an X bar down here. So I have an AND gate and a NOT gate. Therefore, I have every gate I need. Second theorem, Fredkin is universal. So we do the same kind of thing. This is that controlled swap gate here. So if I have X, Y, and a 0, then out here I get X times Y. I will only see a ball down here if there were two balls over here. And this is, in fact, motivated by the billiard ball model of computation. And I can also have X, 1, and a 0. So now you can see these two will get swapped if and only if X is 1. And when it gets swapped, then we get an X over here. So this wire is X bar. These are X and X, and they stay unchanged. The point about this X and X, though, is kind of interesting and important for us. There's extra stuff around. We don't just have a NOT gate. We have a NOT gate with extra stuff, and that's known as garbage. Okay? And this garbage keeps on growing as we build our circuit larger and larger. However, there's a theorem that you can make a garbage the amount of garbage needed to reversibly simulate any Boolean is of the order of the size of the circuit, of the width, and not the depth. So that the amount of garbage can be a controlled amount. And hand in hand with this theorem is another important thing, which is implied by that, which I'm afraid I don't have time to prove for you right now, but I will post a proof of this in the class notes. Any Boolean circuit of n gates can be simulated by a reversible circuit of order of polynomial in n reversible gates. And this polynomial grows approximately as n squared. Okay. So reversible, every computation can be made reversible. Microsoft Office could be reversible. Imagine that. So you can run your typing backwards or your spreadsheet backwards. But people don't do that. And largely, we do not do it today because of the need to tolerate errors and become reliable. And so this is also the fundamental story for quantum computing, because quantum computers fundamentally need to be reversible due to the laws of quantum mechanics. And in the next 3 lectures, you will see exactly that, the laws of quantum mechanics, how you think of them in terms of computation, and then why they need to map directly onto reversible computation. And so we'll come right back to this topic, and we'll see how reversible computation subsumes normal classical computation. And because quantum mechanics subsumes reversible computation, it also subsumes all of computation today. But the laws of quantum mechanics are the laws of physics, and therefore the laws of physics govern computation. Isn't that a great ending? I'll see you next time. Peter Shou will give the next lecture, and then we'll be back. Stick around if you want to ask me questions.